shoot. All right, so here's our scatter plot, and I've put our line of best fit on there. The line of best fit has a slope, got a rise and a run, and it has a y-intercept, which is where it crosses the y-axis. And so we can describe that line as y equals mx plus b, if you remember back from algebra, where m is the slope and b is the y-intercept. And generally, we find these two using technology, just like we did with the regression or with the correlation coefficient. Right? There's too much data for us to do it by hand. So I'm going to hop back over to R. In R, the code is LM for linear model, which doesn't always make a lot of sense. Actually, I should do this. There it is. There's our line of best fit. And it was actually pretty close to the center. Obviously, some of the dots are below it, but it generally follows the trend. Again, this is a visual look. That's nice to see that the dots fall pretty closely. If we want to see what the actual values are, what the slope and y-intercept, we can look at the regression. And there's a lot of information in here, but what we really need are this number and this number. That number right there is negative 0.36. That's the y-intercept. And this number right here is 0.415. That's the slope. So if I were to interpret this, and let me, I'm going to write these things down here. So we get y equals 0.416 times length. And I guess I can be a little bit better. I can call this the width. 0.416 times length minus 0.363. The slope is 0.416. The y-intercept is negative 0.363. If I were to interpret this, I would say an iris that has 0 centimeter length petals will have a negative 0.363 centimeter width petal. Does that make any sense? Negative petal width? That's not possible. But R doesn't know what I'm measuring. It just sees a bunch of numbers. It doesn't do any reasoning. It's up to the human to say, of course, that doesn't make any sense because there are no petals that are a negative width. But that's what the y-intercept says. It says if you could find an iris of 0 centimeter length, then it would have a negative 0.363 centimeter width. And then the human would say, of course, that's not actually possible. The smallest length of petal is about 1 centimeter. Right? So that's not something you have to worry about. Every 1 centimeter increase in length is associated with a 0.416 centimeter increase in width. That's what the slope says. It tells you how does the output change as the input changes. Right? If you're 1 centimeter longer, you would expect to be 0.416 centimeters wider. Not exactly, but that's your best guess. You might still be writing that down, sorry. Okay, so in your labs, you're going to be doing this. You're going to be looking at 2 of the quantitative variables in your data set, and you're going to be exploring if there seems to be a correlation between those variables. How strong is that correlation? And can you describe it with a slope and a y-intercept? And then can you interpret what that y-intercept would mean and what that slope would mean? Of course, every regression analysis also comes with the hidden hypothesis tests. And the research question is the slope, or really what we're talking about is the coefficient on the x variable significantly different from 0. And then you can fill out the rest of the hidden hypothesis test. You got your null, which is, nope, it's basically 0. The alternative, which is, oh, it's different from 0. Pick a significance level, 0.05, collect your data, compute that slope, that coefficient on the x variable, do your hypothesis test, and see if the probability of seeing that slope is small enough that gives you evidence that it's significantly different from 0. So in R, it does it for you. As part of it, it's this right there. 2e minus 16, that's 2 divided by 10 quadrillion about, right? 2 times 10 to the minus 16. The probability of observing this slope, if there actually weren't any relationship, is basically 0. There it is again, they show it to you there. Therefore, we can be confident that yes, there is a fact, a relationship, and this is the best number we can use to describe that relationship quantitatively. There is a p-value also for the intercept, but that's kind of meaningless. Because this is telling me, yeah, I'm super duper sure that a 0 length iris would have a width of negative 0.363. But that's meaningless. So in practice, we don't really worry about the intercept much at all. We tend to worry much more about the coefficient. We might worry about what the estimate on the intercept is, but we usually don't worry about its statistical significance. Just the statistical significance on the coefficient for the x variable. So in our case, in the iris data, the p-value was about 0, which is strongly statistically significant. Now, we can be sure that petal length is very related with petal width, and that 0.15 or 0.16 is a great way to quantify that relationship. Okay. All right, so that will give you the tools to attack Lab 4 to get maybe all of the way through it if you want, or at least a large part of the way through it. On Tuesday, we'll talk a little bit more about these ideas. And trying to think what I'll do. So let me pause the video.